Hello, my name is Shelby Harris, and today I'll be talking to you about the thymic education of T cells, or their development. So, an overview of T cell development is that the T cells will start out as hematopoietic stem cells, or HSCs, in the bone marrow that will travel to the thymus. In the thymus, they'll become known as the hematopoietic precursor cell. Once they get into the thymic cortex, the precursor cells will undergo a series of 4 double negative stages so they become a double positive T cell. A double negative is a T cell that doesn't have the CD4 or a CD8 on their cell surface, versus a double positive is where they have both CD4s and both CD4/8s located on their surface. The double positive cells will then undergo a round of positive and negative selection in the cortex and become either a single positive cell. Well, they will become a single positive cell before moving to the thymic medulla. In the medulla, the single positive cells will encounter the air cell and undergo even more negative selection before they finally be released into the body as educated T cells. This process takes about 1 to 3 weeks. To start off with the early development and the double negative stages, the hematopoietic stem cells give will both give rise to both T cells and B cells, but what causes the cells to become T cells is when they come into the thymus, they encounter a Notch ligand on thymus cells, and that Notch ligand is what causes the T cells to choose to commit to becoming a T cell. After Notch activation, the T cells begin their 4 double negative stages, so they're denoted by DN1 through 4. The stages are defined by the cell surface molecules of c-KIT or CD117, CD44, and CD25. The concentrations and the presence of them on the surface will tell you what stage the cells are in. In the first stage of development 1, we have high concentrations of c-KIT on cell surface, positive for the CD44, but we have no CD25 yet. And the first double negative stage is where they first come into the thymus and they still can give rise to any type of T cell. They haven't really chose what type of T cell they want to be yet. So they're still really young and really not educated. So then we go on to the DN2 stage. And in the DN2 stage, we still have high levels of c-KIT. We still have CD44. And now we have CD25. So in between DN1 and DN2, CD25 became present on the cell surface. And in double negative stage 2, the genes for the TCR receptors are beginning to rearrange within inside the T cell. So we're starting to get some rearrangement of the genes. And then after double negative stage 2, we have double negative stage 3, in which we still have high levels of c-KIT, but now we've lost our CD44 from our cell surface. We no longer have CD44, but we still retain that CD25 that we got in stage 2. And in stage 3, they continue to undergo rearrangement, but then they decide on they either going to become a T cell receptor gamma delta or a T cell receptor alpha beta, and most T cells become alpha beta, and those are your regular T cells that we know. After DN3, we have DN4, which is our last stage, and in the last stage, we have low or no c-KIT on our cell surface. We have no CD44 and no CD25. We've lost almost all of our surface molecules to indicate that we have entered the last stage of the double negative process. And in CD4, we have allelic exclusion happening in the genes, and they become double positive, so they gain both the CD4 and CD8 receptors on their cell surface. After we have the double negative stage, we have selections of double positive cells. So we have 2 types of selections that happen. We have positive selection, which selects for thymocytes that will bind to self-MHC molecules but not bind too tightly to them. And then we have negative selection, which is where we have the cells the thymocytes binding to the self-MHCs, but they're binding too strong, so that it will kill them. because we can't have strong reaction to our self-MHCs or we'll get autoimmune diseases. About 98% of double negative positive cells fail these selections and die in the thymus. 95% will die by neglect, so they will essentially not bind to any receptors and they'll just undergo apoptosis inside the thymus because they didn't receive any survival cytokines from binding to the MHC molecules in there. And then about 2 to 5% are killed by the negative selection that they were reacting too strongly to the self MHC, and then they were killed off by the thymus. And then only about 2 to 5% of the double positive, T cells will survive. That they will bind just right to the self MHC molecules on the cell surface, and they will undergo a few different models to become SP or single positive cells. So lineage commitments of single positive cells. So there's 3 different models that they've proposed to explain how double positive become single positive T cells. So the first one in the extruded model, we have double positive cells that are reacting to MHCs on there. So this cell right here, as a double positive, reacted to a CD8. So it's going to become low in CD4 but high in 8, and then it's going to lose the CD4s while regaining the CD8 and to become a CD8 T cell. And then here we have, again, a double positive, but it engaged with a CD4 MHC cell, so it has high CD4 while having low CD8. So it's going to keep the CD4 but lose a CD8 and become a CD4 single positive T cell. Another model we have is this chilastic model, where we have our double positives here, and then they randomly choose to downregulate either a CD4 or CD8. So if they downregulate CD4, then they're going to get low levels of CD4 and high levels of CD8. And if they're able to bind to positive class 1 molecules, then they will become CD8s instead of CD4s. But if they're not able to bind, again, they will not get those survival cytokines and they will undergo apoptosis. And then down here we have, again, a double positive, but it chose to downregulate CD8, so it has high CD4. So if it will bind to class 2 MHCs, then we will have a CD4 single positive cell, and if we don't bind to the class 2 MHCs, we have apoptosis, our cell is killed. The last model is the kinetic signaling model. So if we have a double positive T cell, then we will have an engagement signal coming down. And for this engagement signal, it downregulates CD8, which will give us a CD4 positive cell while having a low CD8 level. If we have a continuous T cell receptor signal, it will keep going in the same downregulating the CD8. So then we will have CD4 positive but a CD8 negative T cell being formed, versus if we have a disrupted signal via the ligand 7, we will have a CD4 negative, CD positive T cell. It will go the reverse of what it went if we wouldn't have continued that engagement signal. So that's just the 3 ways that we think how they become single positive cells. So this is just an overview of the process. So we're in the cortex of the thymus. So we start out with double positive thymocyte. There will be binding to the MHCs down here. Of course, 2 to 5% will have high affinity reaction and they will be negative selected. 2 to 5% will have a low intermediate affinity interaction. They will be positive selection. They will be allowed to go on. Versus 90 to 95% will die by neglect. They're not binding to anything. They're not receiving those cytokines and they're dying. Then we undergo commitment to lines. And we have either a CD4 single cell or a CD8 single positive cell, and then they will travel onto the medulla to undergo more selection. Medulla negative selection of the single positive cells. So after becoming CD positive, they'll travel to the medulla of the thymus. There they will encounter the air protein and the dendritic cells that will have different MHCs on them. Air is really cool because it can express MHCs from all over the body. So even though air is located in the thymus, it can express MHCs from the brain, from the kidneys, from the liver, so that these cells can get an exposure to different proteins from around the body. So they're not just encountering thymic cells. It's kind of like how you're here in college, even though, yeah, I'm majoring in biology, I'm getting a lot of bio classes. I've also have to take like history, English, foreign language, and stuff like that. I got exposed to other things other than biology. So I know there's other things out there in the world besides biology. So it's kind of like that. This is the last part of thymic education of cells. Of course, if they're negative selected, then they die. So if they bind too strongly to air or to any of the dendritic cells that are possessing MHCs, they will, of course, be killed off. Versus if they don't bind or they bind very lightly, then they'll be positively selected and allowed to live and continue on. So here we have our single positives entering in the medulla. They're encountering air. They bind to it, and they're killed off. They encounter dendritic cells. They bind to it, and they're also killed off. But if they survive and they don't bind to anything, then they're going to be allowed to leave the thymus and go on into the body to fight in your immune system. So how do they leave the thymus? So the gene FOXO1 upregulates the expression of the CCR7 cytokine, which directs the mature T cells to travel to the lymph node. So it says, you're being upregulated. We have this cytokine present. We can leave the thymus and go on to the lymph nodes. When they leave the thymus, they're called recent thymic immigrants, or RTEs, and they don't function like mature T cells in your regular body. They are naive T cells essentially, and they're important sources of T cells in people who have undergone like chemo or they're newborns and stuff like that. So they're really big in research. People are really, really interested in research in these recent thymic immigrants. So after all this, the T cells are now in the blood and the lymph. They're now traveling throughout the body. They're encountering MHCs on dendritic cells in the lymph nodes. In the blood, they're encountering antigens and stuff like that to protect your body from infection and stuff. So that's it. Thymic. So the thymus is the home of T cell development. It goes through a bunch of different reactions and stuff, selections to be chose. So it's a highly regulated process. A lot of them die before they get to the end because it has to be really good. If we have cells that can get out and that they're not really educated, they can cause autoimmune diseases. They can cause other things that are not good for your body to have. So yeah, so it's good that we have this check system to keep them in and to keep them highly educated so they don't do that. All right, thank you.